On to section 5.2, title of which is Geometric Transformations. Okay, so we want to draw pictures. To do so, we need to put vectors in standard position. If we say something like all these vectors lie in a plane, then we're probably describing vectors in standard position. Remember, at least in terms of physics applications, vectors don't have a location. You can put them anywhere. All right, then let's put them in standard position. And then we can discuss things like vectors that lie in a plane, vectors that lie along a line, those type of things. Gentle states that a vector represents a point in space. Okay. If you put the vector in standard position, then yes, but vectors in general, they don't have positions. So we can associate a vector in Rn with components x1 through x sub n, with a point in Rn, P, say, with coordinates x1 through xn. Vectors have components, points have coordinates, by representing the vector as an arrow in standard position, that is, with its tail at the origin and its head at point P. In this way, and this is what I call the geometric interpretation. That's more my verbiage than anything that's widely used. But in this way, we can talk about vectors lying in a plane and vectors determining a line and so forth. They must be in standard position. It's been a while, but we talked about cones, vectors in a cone, all that stuff, depending on those vectors being in standard position for the pictures to make sense. And I do like pictures, so I'm willing to pay the price of putting those vectors in standard position. To distinguish between vectors and points, it's common, at least notationally, to represent vectors using square brackets around the components, whereas we use parentheses around the coordinates of a point. In that way, we've got a notational distinction between the two. I've complained about this for quite some time. You know, it wouldn't bother me if they put a little arrowhead over this vector v, or if they made a boldface, both common notations when dealing with vectors, to distinguish the fact that it's a vector and not something else. My main concern in vector spaces are we talking about vectors or are we talking about scalars? It's clear from the context, as well, rumor has it. But if I drag points into the story, now we got vectors, we got scalars, we got points, we got standard positions, we got coordinate axes, a little more robust notation that indicated you have a vector. I would welcome that, actually. In my sophomore linear algebra approach, here's a link to some of the notes. The first thing we do is talk about vectors as arrows and so forth. But they have to be in standard position to relate them to points, and we get the best pictures, in a sense, when those vectors are drawn in standard position. And we use a better notation than this. We'll either put little arrowheads, the notes are typed up with arrowheads, and if you handwrite it, you have to put arrowheads over the vectors. And the book that I like so much actually represents vectors with boldface. But that's hard to do by hand, so I type the notes up with it in terms of little arrows over them, which one must do when first encountering this stuff. In a linear algebra class, be it taking or tutoring, you'd want to distinguish between vectors and scalars, because these are some new ideas to the folks being exposed to that in a linear algebra class. Probably they've been exposed to it in some sort of physics setting, but you're doing it more formally in a linear algebra class. Vectors and points in Rn, hey, they're different. I think we've had this conversation before. Vectors can be added together. They can be multiplied by scalars, but they don't have a location. Points, you can't add points together. You can't multiply points by scalars, but they do have a location. So the one thing that a point has is something vectors don't have. So there's a big difference between points and vectors. There's a natural relationship between them. Given when you put the vector, when you put the vector in standard position. That is, you put the vector with its tail at the origin, draw it as an arrow. Then the components of that vector will yield the coordinates of a point that lies at the head of that vector. So there's the natural or the geometric relationship between points and vectors, but they're definitely different things. All right, we're going to look at some particular kinds of transformations. A transformation that preserves lengths and angles is an isometric transformation. This word isometry may appear in some other settings, literally meaning same measure. So it's a distance preserving mapping, maybe when you encounter it in terms of analysis, depending on what the space is you're dealing with. You might be in a metric space, for example, where an idea of angles just simply doesn't exist. Well, it does in Rn, does in inner product spaces, in fact. But the term isometric transformation is being used here, not to be confused with maybe some applications of that word isometry in other settings. Here we're getting preservation of both lengths and angles. Ultimately, we're really getting preservation of inner products, and the inner products induce distances, induce a norm. A transformation that preserves angles is called an isotropic transformation. A transformation that doesn't preserve angles is called anisotropic. A transformation of the form that takes vector x to the vector x plus t, t also being a vector, say this happens in Rn, is called a translation transformation. So you're simply taking a vector and moving it using vector addition. I want to say moving it at an amount t. Need to be a little bit careful with how that's interpreted. We've seen pictures of this earlier. You're familiar with linear transformations from linear algebra. Hey, linear transformations are represented by matrices. This translation thing, we're going to have a problem with interpreting that as a linear transformation. Gentle states that all transformations in this section are linear transformations because they preserve straight lines. All right, first off, what's up with a straight line? If anything, I would mean that a straight line in a vector space is a translation of a one-dimensional subspace. The lineness requires that those vectors be put in standard position and all that stuff. You don't have that geometric interpretation unless those vectors are in standard position. Also, that ain't what linear transformation means. I dislike that. We're going to try to deal with transformations using matrices, but it's going to require a trick and a translation into a new setting. So that tells you right there, this is not simply matrix multiplication that will represent transformations. Translations. Translation transformations are not represented by what's traditionally called linear transformations. I'll agree with Gentle. Yeah, if you take a line and translate it, it's still a line with the appropriate interpretation of standard position. But translations are not linear transformations in the following sense. This idea of preserving lines, that's unusual. You often hear, and this ain't the first or the last time you'll hear this, I'm sure, linear transformation mapping, say, Rn into Rn, is usually defined as satisfying T of Ax plus By equals A T of X plus B T of Y. A and B are scalars, X and Y are vector, say, in Rn. That's very much the usual definition of linear. Linear transformation should satisfy that, and translation transformations, they don't satisfy that. So they're not linear transformations in this sense. And this is a much broader sense than this thing Gentle is talking about on page 175 about preserving lines. When we have a linear transformation of this sort, 0 has to be mapped to 0. Plug in X and Y, say, plug in A and B or the 0 scalar. So we'd have to hold for those as well. Then we'd have T of the 0 vector equals 0 vector plus 0 vector. T of the 0 vector has to equal the 0 vector. Well, a translation moves things, and a translation of adding, this is effectively translation, adding a vector t is not going to satisfy this condition unless t is the zero vector, in which case your translation is by nothing, by the zero vector. You're not translating. It's an identity transformation, if you like. So translation doesn't satisfy this more widely used definition of linear. So you know from linear algebra, all linear transformations, say from Rm to Rn, can be represented by n by m matrices. There's a link to some notes from linear algebra. But translation doesn't satisfy the highlighted definition of linear that we use in linear algebra. Okay, so translation is going to cause a problem. We can't represent that simply by matrix multiplication unless we do something weird, and we're going to do something weird. We're going to introduce some new coordinates, but it's not straight matrix multiplication, so we're not violating anything you know from your past. All right, we're going to start out with rotations. I kind of like this stuff because I can draw pictures. The examples we draw are in R2. We'll refer to some rotations in R3. Hard to make pictures of those, but it's not that hard to visualize. Extending to higher dimensions, we're not going to bother. We're just going to stick in R2 and R3. Consider a vector x in R2 with components x1 and x2. So here's that vector in R2, drawn in standard position. We represent it as the arrow in blue in the picture. We now find a transformation that rotates vector x about the origin through an angle theta. So we want to take this vector x, rotate it about the origin through an angle theta. That'll yield this image. When we get the image of vector x under some transformation, we're going to denote it x tilde. So this will be the notation used in this section. Let phi be the angle that vector x makes with the x-axis. Sorry for all the x's. That one's a vector. It's just coordinates system we've introduced. So let phi be the angle associated with x. With that said, then these coordinates x1 and x2, from your knowledge of the unit circle and trigonometry, the x1 coordinate is the length of that vector times the cosine of the angle. If it were polar coordinates, you'd say something like this coordinate here is r cosine theta, this coordinate here is r sine theta. Okay, we don't have r's, we've got the norm of that vector, and we don't have thetas in this role, we have phis. But the same kind of thing you'd see in polar coordinates is trig. The x1 coordinate is norm of x times cosine phi. The x2 coordinate, y coordinate if you like, is the norm of x times sine of phi. Okay, we want to rotate through an angle theta. We're going to let x tilde represent that vector and let the, say, the coordinates of the point we're talking about up here, if this represents a point, the vector's in standard position. So this could represent, it's ambiguous really, this could represent the point or the vector. We're going to use parentheses for points and vectors, as Gentle does. But we get an x1 tilde and an x2 tilde. Oh, and they're going to satisfy the same type of equations for the angle that x tilde makes with the x-axis, which is actually the sum of these two angles. Nothing wrong with my picture in terms of lacking generality. Phi could be negative, and we'll still have the same relationships in terms of adding angles that we're going to talk about. The angle between the positive x-axis and x tilde is right, phi plus theta, even if some of these angles are negative and so forth. So, as above, we get x1 tilde, the first coordinate of this point at the head of vector x tilde when in standard position, is the norm of x times the cosine of phi plus theta, just like we had upstairs. Remember, maybe you want a norm of x tilde. Well, we didn't stretch the vector, we just rotated it. So the norm of x tilde and the norm of x are the same. So this is what we had above. It's the norm of the vector times the cosine of the angle it makes with the positive x-axis. x2 is the norm of the vector times the sine of the angle it makes with the positive x-axis. So we get these representations for x1 tilde and x2 tilde, we're going for representing this transformation with a 2x2 matrix. And quite likely you did this in linear algebra, or it's in your book at least. The summation formula for sine and cosine, recall cosine of phi plus theta and sine of phi plus theta are given in terms of sines and cosines of phi and theta as given. Just for something to look at, because the summation formulas for sine and cosine may not be on the tip of your brain. But upstairs, we had, in the paragraph at the top, we had the cosine, here we go, we had the cosine of phi and the sine of phi in terms of x's and x1's. Rearranging, we get the cosine of phi as x1 over the norm of vector x. Sine of phi is x2 over the norm of vector x. So we can substitute in for pieces of these. The trig functions involving phi, we can substitute in. So we're going to get x1 tilde is the norm of x out front, times the cosine of phi plus theta. Okay, that's all this stuff here. Cosine of phi is x1 over the norm of x1, substituted in there. Cosine of theta, I'm kind of stuck with that because we don't know anything about theta. Minus sine of phi was x2 over the norm of x. Sine of theta, kind of stuck with that. If you'll distribute the x1 norm, the norm of vector x through, we lose those denominators and it produces this, x1 cosine theta minus x2 sine theta. It was a little linear combination there, if we knew theta, of the components of the x vector. Similarly, substitute in for the sine phi and the cosine phi and the sine of phi plus theta formula, expressing x2 tilde in terms of those things, expanding, simplifying, you'll get this. So we're going to define a matrix A inspired by this little trig argument. Define matrix A to have the entries as given here, cosine, negative sine, sine, cosine. Hey, that's this. It's cosine, negative sine, cosine, sine. Then we can express x tilde as A times x. If vector x had components x1 and x2, treat it as a column vector, remember. We do our row times column thing. We get cosine theta times x1, right, minus sine theta times x2, right. And similarly for the second row times the column vector. So we can represent that rotation through an angle theta by this little matrix here. By the way, that's an orthogonal matrix, ain't it? How about we check to see if the columns form an orthonormal set of vectors. To find the magnitudes, we take this squared plus this squared, square root of, square the components, take a square root. Yeah, that's cosine squared plus sine squared. 1, square root of is 1. This, when you square, the negative sign, of course, gets absorbed, and this is sine squared plus cosine squared. Yeah, they're both unit vectors. How about we take a dot product of the two columns? That'd give us cosine times negative sine plus sine times cosine, indeed 0. So this is, in fact, an orthogonal matrix, easy to confirm, it's 2 by 2. Now, we want to rotate sections about rotations. We want to rotate about, say, the y-axis. So we want to do some rotations in 3 dimensions about axes. Here's the story on rotating about the y-axis. The claim is we're going to use this. So I would expect to be able to take this and compare it to what we had upstairs. There's rotating about the y-axis. All right, that's going to leave y coordinates fixed. So that's the reason you see this 0, 1, 0, 0, 1, 0, this second row and second column. More of that in a second. But I'd expect to see a cosine, negative sine, sine, cosine. I don't. I see cosine, positive sine, and negatives down here, cosine. What happened? What's up with that? How can I without working this from scratch. Use this information to inspire this as an appropriate matrix that rotates things about the y-axis. Okay, let's try the following on. The reason for the signs of the signs, the SIGN of the SINE, the reason that one's not negative and that one isn't positive is the following. In a right-hand coordinate system, okay, so in your mind, visualize, I'm going to try to give you a state-of-the-art visualization here in a second. Imagine a right-hand coordinate system. We're going to rotate the XZ plane into the XY plane, and then we can use that matrix A that we had a second ago. So what we're doing is rotating the positive Z-axis on to the positive Y-axis. Then a positive angle in the image represents a negative rotation about the y-axis. Okay, let's try this out for a second. So what you're going to do is take a right-hand coordinate system. Here's a right-hand coordinate system. Here's a pretty good perspective. Okay, we'd have the x-axis, the y-axis, and the z-axis. X, Y, Z. So here's the XZ plane, index finger and thumb. We're going to rotate that into the XY plane, index finger, middle finger, horizontal plane. So what we'll do is just rotate it over. The x-axis stays put. Point it right at the camera, right? The x-axis stays put. And the z-axis rolls over into the horizontal plane. And now the y-axis is pointed down. Okay, when we set things up in the XY plane originally, we rotated things about the origin. We could have introduced a z-axis there and said the z-axis, it would have to point straight up. Here's where the negative sign comes from. When we do that transformation, we've got the y-axis pointing downward, not upward. The positive y-axis points downward, not upward. And that's the problem. So let's try this again. A positive angle in the image after the rotation has been done represents a negative rotation about the y-axis. That's because when we interpret it in terms of those rotations, the y-axis points down, not up. So I can't use exactly what we had here. I got to replace theta with negative theta, because the y-axis is pointing down, not up. And I'm going back to this original picture. Imagine a z-axis coming out of the origin there. It'd have to come out towards you. The positive z-axis would have to come out towards you if this is in fact a right-hand coordinate system. By doing that rotation, we've actually got that vertical axis. By doing the rotation, y becomes the vertical axis, and it's pointing in the wrong direction. So we got to change signs of angles if we're going to use the formula up there. And I've got to replace theta with negative theta. No great loss. Cosine's an even function. Cosine of negative theta is cosine theta. Apply that in both places. Sine's an odd function. Sine of negative theta is negative sine theta. So we pick up a negative here and a negative here, giving a positive here and a negative here. We already had a negative there. So that's where the distribution of the negative signs are coming from. And that's the reason we get a rotation about the y-axis is represented like this. So we keep the y coordinates the same, and then think about applying what we had up there, but we've created it in such a way that we have to replace thetas with negative thetas to get this type of representation. Here's a rotation represented in terms of a matrix, rotating about the y-axis. I see some neat stuff in the second row and second column, and we're talking about, the second axis, as it were. I'd expect to see the same type of thing. Similarly, if we were to rotate about the x-axis, we'll get first row, first column, as probably anticipated. And we get the cosine, negative sine, sine, cosine distributed in this form. And about the z-axis, we can actually here, this is the cleanest one, to recycle what we had from the matrix A up top. Right, this didn't discuss anything about z coordinates because we were having a conversation in the xy plane, but it just as easily could be applied to a rotation about the z-axis. Angles stay the same, and we do get the cosine, negative sine, sine, cosine. We get that same little pattern in these two. It was the y-axis that introduced that extra negative sign for reasons explained. Eulers' rotation theorem implies that a rotation in R3 about any axis through the origin is a combination of rotations about the x, y, and z axis. So the claim is any rotation about an axis through the origin in R3 is a product of these matrices B, C, and D. We could vary the theta, and that gives us a bunch of matrices. So we could let theta range from 0 to 2 pi. That gives you an infinite number of matrices of this type, and of the third type. So anyhow, this is a huge collection of matrices, as it should be, representing rotations. We can take the collection of all rotation matrices of these forms, B, C, and D, or B, C, I didn't label this one, B, C, and this one, and they form a group. A group called the 3D rotational group, or the special, the group of special orthogonal 3x3 matrices, special orthogonal, SO, SO3, 3 because we're having a conversation about 3x3 matrices, or if you like, we're having a conversation in 3 dimensions. So we could form a group out of those rotation matrices, rotating about an axis through the origin. It's an infinite group. We've seen groups here and there in passing. In senior level algebra, introduction to modern algebra, you usually don't study much with the infinite groups, maybe the reals, maybe the rationals. But infinite groups don't play a big role in those classes just traditionally. But here's an example that has a very geometric interpretation. Arguably, it's even some kind of symmetry group of something or other. Symmetry group of the sphere is what it is. The unit sphere in R3. But special orthogonal group, in fact, it's a subgroup of the orthogonal group. I think we mentioned this when we did orthogonal matrices. Take all 3x3 orthogonal matrices, they form the orthogonal group, O of 3. And maybe we're dealing at this point, of course, with real numbers. We could have done something with complex scalars and also talked about orthogonal groups in that setting, but real scalars here. So this special orthogonal group, SO3, it's a subgroup of this more general group of the orthogonal group O of 3. One comment, the elements of SO3 could be distinguished from the other elements of the orthogonal group. In it, they've got a determinant of 1. We commented somewhere in the past that the determinant of an orthogonal matrix is 1. So there's another way to classify that collection of matrices. But gives us a geometric interpretation of the way matrices behave. And hey, since those transformations, those rotations, are represented by matrices, they're linear in the usual sense. You might encounter in linear algebra reflections, maybe in R2 about the x-axis or the y-axis or the line y equals x. These are all examples of linear transformations as well. We're about to generalize that idea to reflections about any line. I've got a link to some notes from linear algebra. There's lots of little pictures there. It's neat stuff because it's visual. And this is too. We're going to take two vectors, u and v. Let u and v be orthonormal vectors, and let x be a vector that's in the space spanned by u and v. All right, so we're busting this down to some picture I can draw on a plane. So we'll take U and V as, take them to be a basis of some two-dimensional subspace of Rn, if we're using n vectors here. But we get a picture that looks something like this. Maybe I put U and V in standard position. And since we're considering the space spanned by U and V, and we've taken X to be a vector in that space, X is some linear combination of U and V. Say X equals C sub 1U plus C sub 2V. Some scalars, C1 and C2. We're defining X tilde equals negative C1U. Make that bigger. I do want to keep the picture in frame though. For X equals this linear combination of U and V, we're defining X tilde, this linear combination of U and V. We just change the sign of the coefficient of U to be the reflection of X about V in the direction, typo here, in the direction U. The reflection about V in the direction of U in a picture is this. We had X in red as a linear combination of V and U. So we could project back and find out what C sub 1 is in this linear combination representation. It looks like it's about a third of the length of U. Looks like if we were to project X onto V, we get, what's that, about 3/4 of the length of V. So we could speculate what these coefficients might be. And you simply change the sign of the coefficient of U. So instead of going upwards in the direction of U, we go downwards in the opposite direction of vector U by introducing that negative sign. And you get a mirror image, you get a reflection. So of course it's called reflection because, look at it, it's a reflection. But this gives us a way to go through and represent reflections, which could certainly be written in terms of a matrix that would do that reflection. What makes it tricky is, I need to know the U's and the V's from the start to go through and set this up. So expressing a general reflection, I need to know a reflection about what. And those rotation matrices we had upstairs could come in convenient in describing general reflections. All right, so these reflections are linear transformations as well. It's the translations that are causing the problem. Translations are not in the usual sense linear transformations, and we're not changing that. We can't represent these with matrix multiplication. You can't take a vector V and translate it by multiplying it by some matrix, unless you're translating it by 0, in which case you're not translating it, I would argue. We're going to introduce a new set of coordinates, which lets us translate, quote unquote, vectors into the new coordinates and then represent translation by matrix multiplication in the new coordinates. Did I read that correctly? Translate in the sense of rewriting it in this new language, this new coordinate system, and then translate in the sense of shifting. Okay, and that coordinate system is called homogeneous coordinates. For point x1 through x sub d and rd, we introduce the homogeneous coordinates by adding a dimension. We're going to call the homogeneous coordinates of that point x sub 0 super h, x sub 1 super h through x sub d super h, where x sub 0 drives everything. We're defining x sub 1 super h to be x sub 0 times the old x sub 1. X sub 2 super h to be x sub 0 super h times the old x sub 2, and so forth. So what we're doing is we're taking that thing there, multiplying all the components. We're talking a point here, point vector. It's actually ambiguous. They both live in RD. We're multiplying these things here by x sub 0 super h and creating these new components or coordinates. Coordinates, if it's coordinates, I'm talking points. If it's components, I'm talking vectors. So we're adding a dimension and putting this new number here. Now, homogeneous coordinates in RD plus 1, represent points in RD. They represent them in a funny way. I got to do some translation. If x sub 0 super h equals 1, then we've just stuck a 1 in the first position and copied all these things down here. The homogeneous coordinates are the same as the regular coordinates for 1 through d. Right? We subscripted the first one with a 0 in the homogeneous coordinate. If x sub 0 h equals 0, then you're going to get all zeros here. Gentle says this collection of all homogeneous coordinates that have x sub 0 super h equal to 0 corresponds to the projective geometry, corresponds in projective geometry to the hyperplane at infinity. Okay, I'm going to leave you to figure out the details on that. I'm happy to say x sub 0 super h equals 0. There's a problem. I'm going to get only zeros out. I can't translate back is what the problem is that creates. Okay, so what we're going to do is represent the translation transformation. That is, it takes vector x and maps it to x plus some vector t, the translation vector. So call that x tilde. We're going to do it as follows. Let x have components, x1 through x sub d. Let t have components, t1 through t sub d. These are vectors. We're adding them together. They couldn't be points. These are vectors. I've fallen back on my sophomore linear algebra notation here of using square brackets for vectors. Doesn't matter whether you use square brackets or round brackets. Unless you got vectors and points in the same conversation, like we have here. And then I really want to distinguish between them somehow or other. So I'm using square brackets for vectors and parentheses for points in this argument. So let x and t have those representations. And what we're going to do is represent translation with matrix multiplication. But you can't do that because a matrix transformation is a linear transformation, and translation is not a linear transformation. Okay, we're going to use a trick, and we're going to use matrix multiplication, not on the original vector, but on the homogeneous coordinates. So what we're going to do is take a vector, translate it into homogeneous coordinates, do the translation using matrix multiplication. There's the matrix we're going to use right there. That'll do the translation, but in homogeneous coordinates. And then we'll take the homogeneous coordinates and translate back. I'm using the word translate in two settings. Rewrite, maybe I should use, we're going to rewrite the vector x in homogeneous coordinates, multiply that by the matrix T at the bottom of the screen. That'll give us a new vector in homogeneous coordinates, and then rewrite that vector back in terms of a vector in RD. So we're going to take a brief excursion to RD plus 1. And what we're dealing with is a d plus 1 by d plus 1 matrix here. That's the plan. That's not what linear is. We're getting linearity in this homogeneous representation. Yeah, you're not getting a literal translation, though, with respect to the homogeneous coordinates. All right, so here's what we're doing. Represent the point x1, x2 through x sub d as one x1 through x sub d. That is, use homogeneous coordinates for this point. Then for d plus 1 by d plus 1 matrix given here, okay, we're taking the t1 through t sub d. That was the components of the translation vector t. Put those components here, otherwise you get yourself an identity matrix. Notice we started with a second row. So indeed, this is d plus 1, and it's square. It's d plus 1 by d plus 1. The vector x super h, okay, this ain't the vector we started with. We've taken vector x and introduced a vector x super h. Why, this is a vector in RD plus 1. It's got the extra component. It's quite similar to this thing up here, but that's a point, and this is a vector. We'll have to transpose it to get it, has to be a column vector to do the matrix multiplication. I just write it like this because it's too clunky to get it to fit in the notes. If I write column vectors, it'll take up too much space. So I transpose it for computational reasons. Then if we'll take T and apply it to this column vector, we're going to get row times column. That 1 won't change anything. We get a 1 for the first entry. Second row, first column, that'll give us a T sub 1 plus X sub 1. So we pick up the X sub 1 here. The T sub 1 will hit the 1, producing a T sub 1 times 1. The 1 hits the X sub 1, producing a 1 times X sub 1. We get an X1 plus T sub 1, rearranging, and an X2 plus T sub 2 up through an X sub D plus T sub D, similarly. So we've taken this homogeneous vector and produced a new homogeneous vector. Let's call it X tilde H. Now, problem is that vector lives in Rd plus 1. We want to talk about a vector in Rd. We're trying to get to this vector up here. We're trying to simply translate vector X by adding the vector T to it, adding these components to the components of X. And we're trying to do it with a matrix multiplication. So that's how we got into this situation. Okay, so we've got the X tilde H. It's associated, put it in standard position in Rd plus 1, the natural association, the geometric interpretation. It's associated with this point that has as coordinates the components of the point X super H tilde. So this is the homogeneous coordinates associated with the vector X plus T, or X tilde, in Rd. So how do you get that vector back out? Drop the 1. Since it's a 1, if it was something different, we'd have to do some division potentially. But just drop the 1, and that'll give you the translated vector. Therefore, translation by any vector T in Rd is represented by matrix multiplication by T, but you had to take the vector X upstairs somewhere, write it in homogeneous coordinates, that is, translate it, convert it, associate it, rewrite it in homogeneous coordinates. Then do the multiplication with a matrix, producing an output, X tilde H, and then you had to translate back, or convert back, or associate back, or rewrite back. So X to X tilde super H, matrix multiplication. Nope, I messed up. Let's see, X to X super H, matrix multiplication to X super H tilde, and then to the transformed, the X tilde vector. It's a trick. That's what it is. It allows us to perform this matrix multiplication by hopping into a higher dimension. And odds are there's some, probably some type of geometric interpretation to this as well. I didn't think ahead on that, but I know there's some geometry behind it. It's matrix multiplication in a bigger space. With all this, Gentle does say, we must be careful to distinguish the point X from the vector that represents the point. And yeah, I second that emotion. There's a big difference between vectors and points. He's bouncing between vectors and points and components and coordinates in what he's set up here. But there's my version of what he's presented there. And that'll do for geometric transformations. And so we'll look at other transformations in the next few sections. These sections in Chapter 5 are mercifully shorter than some of those we've dealt with earlier, especially in Chapter 3. So onward to section 5.3. Have a nice day.